Hey, welcome back to Calculus. In this short video, it's a little bonus video as we wrap up our work in section 7.8. I want to tell you about something that people in mathematics and calculus circles usually call Gabriel's horn, or sometimes it's called Torricelli's trumpet. It's got a little bit more of an alliterative name to it. So what is this Gabriel's horn? Well, let me tell you. Story starts by taking the region under the graph of f of x equals 1 over x. So we're going to take that reciprocal function and look at its graph over the entire interval from 1 to infinity. Okay, and we're going to rotate that region around the x-axis and to form a solid. So I've got the region R here drawn. It's this gray region, but I'm indicating it never stops. So we're looking at this from the interval from 1 to infinity, and we're going to rotate that thing around the x-axis. Let me remind you, before we look at a picture of what that might look like, that that area R itself is infinite. The integral from 1 to infinity of 1 over x diverges. Yeah, so R has infinite area. I'm just going to briefly write that like this. It's the integral from 1 to infinity of 1 over x dx diverges. So the region that I'm rotating around this x-axis has infinite area. Okay? So here's what a solid would look like, or at least the surface of it. So you can kind of imagine I've got my axes labeled here. Here's my x-axis and my y-axis. This axis is just coming out of the xy plane so that we can rotate. But you can kind of still imagine that region R. I kind of draw it in here with my laser pointer. It's bounded by that curve 1 over x. And you rotate that thing around the x-axis and you form this solid. And people usually call this solid, Gabriel's horn. Or as we just saw, Torricelli's trumpet. You can choose either one. Let's calculate its volume. I don't want this video to be long, so I wrote out the stuff before we do it, but the volume of this thing, I'm using washers. Yeah, I'm using, or it's actually disks, there's no hole in it. So I'm using the disk formula. So I've got pi times my function value squared, and I'm integrating that from 1 to infinity. All right, and we'll make quick work of this. I'll just let you check it out. I'm writing that as a limit as t goes to infinity of the integral from 1 to t, because that's what these improper integrals mean. Okay, take my antiderivative of x to the negative 2. It's negative x to the negative 1. I'm evaluating that from 1 to t, taking the limit. Put the pi out in front of the limit. Okay, so I have pi times this limit. Once you evaluate that thing, it's minus 1 over t minus a minus 1 or plus 1. So you just end up getting pi, and that would be whatever the distance units would be cubed. So the volume of Gabriel's horn is finite. It has a finite volume. I think that's kind of interesting. This infinite region, R, gets rotated, infinite area, gets rotated around the x-axis to sweep out a solid object, which again is an unbounded object. There are points inside of Gabriel's horn, arbitrarily far out, arbitrarily big x-coordinates, but its volume is finite. It's kind of interesting. Just sort of summarize that here in this picture. The area under the curve is finite. So the area of the region R is infinite. It's not a finite number. R is an infinite region. Remember, it's unbounded. It continues from 1 all the way out to infinity. But the volume of the solid that it generates is finite. In fact, it has pi cubic units. It's kind of perplexing, paradoxical, interesting thing to think about. But there's even more. It gets even better. We're not going to cover this in this particular section of Calculus 2, but in section 8.2, there's an application of the definite integral called surface area of solids of revolution. So in that section, it can be shown that the surface area of this solid of revolution is given by the integral that I've got written in the middle here. So I won't even pronounce it all out loud, but the surface area of that thing, I'm not deriving it here, but it's given by that integral. Okay, that integral can be somewhat difficult to compute, to evaluate it directly. right? So to say what that number is or isn't, if that interval converges or diverges, finding an antiderivative for this integrand can be a bit of a challenge, but we don't have to evaluate it directly. We're say interested in knowing if it converges or diverges. If I take my integrand, my square root of x to the fourth plus 1 over x cubed, can you guys stop the video and say why would I know that that is bigger than the square root of x to the fourth over x cubed? Stop and answer, but I'm just going to continue. The reason is because, well, this fraction on the right here, its numerator is smaller, and a smaller numerator makes smaller fractions. Okay, and then I'm just algebraically simplifying this thing. The square root of x to the fourth is x squared over x cubed is 1 over x. So the integrand of my improper integral here is strictly bigger than 1 over x, the integrand of a known to diverge integral, right? The integral from 1 to infinity of 1 over x diverges from our work in section 7.8. So I know that the surface area integral diverges by the comparison test. All right, I'm comparing it to the known to diverge integral from 1 to infinity of 1 over x. Nice. So to kind of wrap it all up, this object is sort of this interesting thing, Gabriel's horn, Torricelli's trumpet, whatever you want to call it. You generate it by revolving a region that has infinite area. So the region R had infinite area. We revolve it around an axis and we get something with finite volume, but it has an infinite surface area. Yeah, so it's kind of this interesting object. So I'm going to end this video with just a question. Imagine that you created the surface of this Gabriel's horn with something porous like paper. And then we fill it with paint. I'm just going to put dot, dot, dot. I could fill that with a finite volume of paint, pi cubic units of paint. And then that paint would seep through the paper. The paper is porous. So in some sense, I've painted an infinite object with a finite amount of paint. I don't know. It's perplexing. Anyway, I hope you liked this. Thanks.